Section 5.1, the natural logarithmic function, differentiation. In pre-calculus, we learn an algebraic approach to logarithms. For example, in the equation 2 to the third power equals 8, we denote the exponents 3 by log base 2 of 8. So the definition log base b of x equals y is equivalent to b to the y's power equals x. In pre-calculus, we set the function f of x equals b to the x power and g of x equals log base b of x are inverse of each other. The number b is called the base of the logarithm. The logarithm of base e is called the natural logarithm, which is abbreviated ln. In today's lesson, we're going to take an algebraic approach to the natural logarithm. The natural logarithm function is defined as an integral from 1 to the variable x, 1 over t dt, where x is bigger than 1. Geometrically, it means the net area for the curve 1 over t in the interval from 1 to x for any x bigger than 1. Note, the integral is not defined for x less than 0 because we have an infinite discontinuity at x equals 0. But for x equals 1, ln of x is simply the integral from 1 to 1 over t dt, so it will equals 1. Therefore, we have ln of 1 equals 0, which is consistent with what we have learned from pre-calculus. How about for x is between 0 and 1? Well, take a look at this integral. ln of x equal integral from 1 to x, 1 over t dt. If we switch the integration limits, the integral will become a negative of integral, the definite integral from x to 1 over t dt. And from the picture we can see it's a negative area, so it's less than 0. And all this property is consistent with what we already know for the function ln of x from pre-calculus. Recall the fundamental theorem of calculus, part 2. Let f be continuous on the interval ab, and let the new function g be defined by integral from a to x f of t dt, where x is in the interval ab. We can say that this integral is continuous on the interval ab and differentiable on the open interval a comma b, with g prime of x equal the integrand f evaluated at x. Apply the fundamental theorem of calculus to the natural log function. Take the derivatives with respect to x back to x of the function of x, which is the natural log function. It's the same as integral from a to x with respect to x of its definition, integral from 1 to x, 1 over t dt. Apply the fundamental theorem to the natural logarithm function with the integrand evaluated at x. So we have 1 over x. Therefore, the derivative of natural logarithmic function d over dx ln of x equals 1 over x. Using the definition of L1 of x as an integral and the property of integrals, we can derive the following laws of logarithms. If a and b are positive numbers and r is a rational number, then L1 of a times b, a times b, L1 of a plus L1 of a plus L1 of b. Ln of a over b equals Ln of a minus Ln of b. And Ln of a to the r's power, we can take the power out, it will equals r times Ln of a. Let's use this property which we are familiar with from pre-calculus to do the following examples. Example number 1, expand Ln of x to the third power times square root of x plus 5 all over x squared plus 4. So because we see a quotient, we will apply the log of a quotient, which will become a difference of logs. So we get Ln of the numerator x cubed square root of x plus 5 minus Ln of the denominator x squared plus 4. We are not quite done yet because we do see a product right here, x cubed times square root of x plus 5. So it will become Ln of x cubed plus Ln of, we can rewrite the square root as the 1/2 power. So x plus 5 to the 1/2 power, subtract Ln of x squared plus 4. And finally, we take out all, any rational powers. So for the first term, we have 3 Ln of x. Second term, we have 1/2 Ln of x plus 5. And lastly, we have Ln of x squared plus 4. And we cannot factor x squared plus 4, so we are done in expanding this expression. Let's study about the graph of Ln of x function. It can be shown that as x goes to infinity, Ln of x equals infinity by looking at the graph of 1 over t. The area as x goes to infinity is going to be infinite. And as x approach 0 from the right, this is 1 and x is right here, it will be the negative of this area. And this area as x goes to 0 is approaching infinity, so we get the limit as x goes to 0 from the right, Ln of x equals negative infinity. Now for x bigger than 0, the derivative of the natural log function is 1 over x, which is also bigger than 0. So y equals Ln of x is increasing. On the interval 0 to infinity. And this is the knowledge that we learned from calculus 1. And for x bigger than 0, if we take the second derivative, according to the power rule, we get negative 1 over x squared. And 1 over x squared is always positive on the interval 0, infinity. So the negative of a positive number will be always less than 0. The second derivative is less than 0. implies the original function is concave down on the interval 0 to infinity. Therefore, we observe the property when x equals 1, ln of 1 equals 0. And it's an increasing function. It's increasing as x goes to infinity, and it's approaching negative infinity as x approach 0 from the right. So this is the graph for y equals ln of x. Next, we're going to learn about the number e. Because ln of 1 equals 0 and y equals ln of x is increasing to arbitrary large values, the intermediate theorem that we learned from calculus 1 guarantees that there is a number x such that ln of x will equals 1, and that number is called e, and we can calculate e is approximately 2.71828 and so on. Note that e is an irrational number. It cannot be written as a decimal that ends or repeats. And this is where the value of e comes from. Next, we will use the property of the derivative of ln of x combined with the chain rule to calculate derivative involving the natural log function. For example number 2, find the derivative with respect to x for y equals ln of 2x to the 5th power plus 3x. The derivative dy with respect to x will equal, according to the chain rule, we take the derivative of the outer function, which is 1 over the inside function, so it's x, 2x to the 5th power plus 3x. By the chain rule, we need to multiply by the derivative of the inner function, which is 10x to the 4th power plus 3. And this is the derivative for example number 2. Now let's take a look at example number 3. Again, we need to find the derivative of the function with respect to x. And we will take the derivative of the outer function. Natural log function has a derivative 1 over inner function, cosine of x, multiplied by the derivative of cosine of x, which is negative sine of x. And if we simplify it, we will get negative tangent of x, because sine over cosine equals tangent. Now how do we find the derivative for f of x equals 1 over ln of x? It might look confusing to begin with, but if we take a note at what is the inner function and what is the outer function, it will make it much easier to apply the chain rule. So f of x equals, outer function is 1 over the inner function, so we get something to the negative 1 power, and the inner function is ln of x. So in order to find f prime of x, we apply the chain rule we apply the power rule first. Power comes down, power decreased by 1 times the derivative of the inner function, 1 over x. And if we want to simplify it, we will get negative 1 over x times ln of x squared. Next, we will find the derivative for x squared times ln of x. And in this case, since it's a product, we will apply the product rule. F prime of x equals derivative of the first function, 2x, times the second, plus derivative of the first function times the derivative of the second, 1 over x. To simplify, we get 2x times ln of x plus x.